Well, see, in this lecture, we will see how to calculate the mechanical work, I mean PV work, and what is the meaning of PV work, what is the driving force in the PV work, right? But before going into the detail of PV work, first we will see in physics you have gone through different types of work like mechanical work, right? Like mechanical work. Mechanical work is equal to F force external into displacement, right? dl, right? Similarly, if you take dl is the displacement, F external is the external force, right? Similarly, if you take gravitational work, right? Gravity work is equal to mg dh. So dh, the difference in height between 2 points, you can take, right? Similarly, if you take, electrochemical work, hmm, electrochemical work. So this is equal to delta V potential difference into dq, or delta V into I into dt, right? So it is clear that this is a potential difference and this is the charge. So, and I current into time, right? So electrochemical work you can calculate by using this. Similarly, we have expansion oblique compression work. Expansion oblique compression work, popularly known as PV work, this is equal to minus P external into dV. See, this is a master formula and this negative sign, this is a convention basically. This is a convention, right? So, see this PV work or this any kind of work, whether it is a path function or a state function, it depends on the nature of force involved in that work, right? So some work are state function, some work are path function. Here we are, mainly focus, not only focus, mainly we focus on the PV work, and PV work is a path function, right? Means this PV work depends on the path followed by the process, okay? So basically work is path function or state function. It depends on the nature of force. If force is conservative, if force is conservative in any work, then the work is state function. And if force is non-conservative, then it is what? Path function. So what is force here in this PV work, right? So in PV work, in PV work, pressure volume work, the pressure difference, the pressure difference difference between system and surrounding is the driving force. Driving force, and it is non-conservative. Non-conservative. And if force is non-conservative, then the work is path function, right? It is not a state function. So this is the reason why this PV work is what? Path function. It depends on the path followed by the process, right? Means if you change the path of the process, work is different. Means work will change, right? So in all these work, the force is conservative, and therefore this is what state functions, right? So here PV work is clearly a path function, and it depends on the path followed by the process. And this negative sign, it is a convention, and this convention basically derived from that sign convention what I have taught you in the previous lecture, that energy change of the system, right? So that this if you don't put here this negative sign, you cannot justify the above discussion what I have told you, right? So this is the default formula. I can say this is the master formula for the calculation of PV work. Now you can change in this formula and make the different formula for different processes. For example, reversible process, irreversible process, like that, right? Now we can see how this formula we can visualize. Suppose that this is one system which is given to us. This is initial state, and this is final state, right? So in this case, what is happening? Expansion is taking place, or compression is taking place. Obviously compression is taking place. So for compression, expansion or compression, both formula is same, right? So suppose that this is what this time V1 is this. So this is V2. So since V2 is less than V1, means compression of gas takes place. First information. Second information, P external is more than P gas, right? Here P external means external pressure is more than P gas, therefore the piston is shifted. Now this piston is shifted, this L, so work is equal to what we can write here, W is equal to F into what? L, F dot L. we can write. This is the applied force and this is the distance, right? This is the basic formula. And for expansion or compression, we can write F is equal to P external into A, right? So we can write here work is equal to minus, this is convention, I am putting this from my side, minus P external A into what? This DL we can say. This you can take DL, right? F in place of F we can put P external A into DL. So A into DL is equal to, we can write here delta V. So this is equal to minus P external delta V, right? So this is the equation 3 and this is the what? Basic formula, or we can say master formula for calculation of PV work. Main formula for calculation of PV work, right? Now see, I am taking different situation here, reversible and irreversible, and I am imposing different condition. So first I am taking calculation of work in isothermal thermal reversible expansion oblique compression of an ideal gas, right? So first case I am taking thermal calculation of work in uh, reversible reversible expansion or compression of an ideal gas, right? Suppose that so see isothermal reversible expansion oblique compression. So all the conditions should be fulfilled here. So if a gas expands isothermally and reversibly, so in this case, if the process is reversible, then what will happen? What we can write that suppose that in this case there is a very slow process. When this process is very slow, when this piston is will move slowly, down, when there is a little difference between external pressure and pressure of gas. So you can write here, or we can write here, P external is equal to P gas plus minus dP, right? And This is the equation for reversible change. For reversible change, right? And dp tends to 0. dp tends to 0, so the process is relatively slow. Relatively slow. So this process is very slow. Okay. So we can write here that P external is equal to P gas, right? P external is equal to P gas, we can write here. Now this delta W, initial state to final state, this is equal to minus P external into delta V or dV. This is the master formula, this formula. Now in place of P external, we can put a P gas. So you can write here minus P gas dV. This is equation 2. Now wait for a few second and let's discuss about this P gas. Now tell me, this P gas is variable or it is constant every time? Think. Process is going on, piston is moving down or moving up very slowly. So at every moment, at every instant, your system is acquiring a new pressure. Your system is acquiring a new pressure. So here this P gas is variable between initial and final state. Between initial and final state. Final state. This is variable. Since the behavior of the gas is ideal, so we can write here P gas is equal to nRT by V. Volume is changing, moles are constant, so here we can put minus nRT dV by V. N is constant, R is constant, T is constant because isothermal process is there. So now your equation, now it can be integrated between these two states. So this delta W 1 to 2 reversible. This is reversible, right? And this is also reversible. So what is the integration of this? The integration of this is a path function. So integration of this is simply W reversible. This is equal to, integration of this is minus 2.303 nRT log base 10 V2 by V1. So this is the formula for the calculation of work in isothermal reversible expansion or compression. Since temperature is constant, N is constant, so we can write here P1 V1 is equal to P2 V2, Boyle's law. So this equation can be rewritten in a different manner. Minus 2.303 nRT log P1 by P2. Right. So whenever initial volume and final volume is given, temperature is given, quantity of the gas is given, so you can very easily calculate how much work is involved, right? See, when V2 is greater than V1, V2 is greater than V1 means expansion. So whenever expansion is taking place, right, expansion is taking place, then this W is negative. W will be negative. W negative means this work is negative, V2 is greater than V1, means the work is done by the system. Means work is done, work is done by the system. Means the energy of system is decreases. So, and if V2 is less than V1, then compression is taking place. Compression is taking place. This time W is positive, means the work is done on the gas by the surrounding. The work is done on the gas. On the gas, and this will increases the energy of the system, right? So this formula you can use for the calculation of work in isothermal and reversible expansion, right? Isothermal and reversible expansion. Clear to everybody? Okay, good. Now we can take this irreversible expansion of the gas. So if we take irreversible expansion of the gas and isothermal, the second case, right? So in case of irreversible process, when you take irreversible process, so in case of irreversible process, the P external is always constant, right? Because in the irreversible process, your process is fast, and you just shifted the piston, and finally when your system is under equilibrium, so finally your gas pressure is always equal to the external pressure. So when I'm telling about the external pressure, means external pressure may include atmospheric pressure and some other pressure as well, right? So in irreversible process, this is the point of difference, that P external in irreversible process, in this process, in this process, expansion oblique compression always takes place at constant external pressure, at constant external pressure. Means every time when your system, you have taken a system and you have shifted the piston, so finally when your gas is in equilibrium with your external pressure, means external pressure of the system, external pressure of surrounding. So in that situation only we are calculating the work, because there is no intermediate step between initial and final state, right? And if suppose that few steps are there, so but it is relatively fast, means when you are taking the reversible process, then it will complete it in infinite steps, but irreversible process, that will complete in what, uh, 2 or 3 steps, right? So in this case, every time P external is constant, means P external is constant, right? Because we are not considering the intermediate steps here, right? So W irreversible is equal to, between initial and final state, is equal to minus P external, which is a constant, 1 to 2 delta V, right? This is the equation. So this time you will get minus P external V2 minus V1. Now you can replace here P external, here you can write nRT by P2 minus nRT by P1, right? So we can see this is the W irreversible. Here P1 is the initial pressure of the gas, initial pressure of gas. P2 is equal to the final pressure of the gas, and P external is the external pressure, external pressure. P external may or may not be equal to the P2. P external may or may not be equal to P2, right? Means this P2 final pressure of the gas may or may not be equal to the external pressure. It is not mandatory that every time this should be equal. It may or may not, right? That depends on our construction of our system. So this is the two formula we have for calculation of work in irreversible process, right? Right. So by using this formula, you can determine, or you can calculate the work in irreversible process, and by using this formula you can calculate in the reversible process, right? Now see, I have considered here reversible and irreversible path. between same initial and same final state, if we compare that, if we move reversibly and if we move irreversibly, so the path of irreversibility is this. First, you change this, suddenly change the pressure. You start from here and stop here. Means suddenly you decrease the pressure. Means suddenly you can push the piston up and fix at this pressure P2. And then volume, you should consider volume is constant in this change. And after that, this pressure is constant and gas is now expanding. See, imagine if you are suddenly pushing the piston of any gas cylinder, there is a chaos inside the cylinder. Different patches will form with different region, with different pressure, and with different, temperature. When you allow them to make the equilibrium, after that it will form the, mechanical equilibrium inside the system and with the surrounding of the system, right? So this is the representation of irreversible expansion, and this is the representation of reversible expansion. So one more way to calculate the work involved in this such type of process. Suppose that initial state is this, final state is this. Here the initial state is this, and final state is this. Same initial and same final state if we compare. So area under the curve, we can use the work involved. So here this area is enclosed by this reversible path, right? So this is a reversible path, and this is the irreversible path, irreversible path, right? So here the area under the curve is this. Area under the curve is this, right? So in this way, you can compare the work involved. So you can say in both the expansion work, the magnitude of work in W reversible is more than the W irreversible. Don't consider the sign here, right? Don't consider the sign. So the magnitude of work involved in the reversible expansion is more than the work involved in the irreversible expansion, right? So it is clear that the magnitude of work in reversible expansion is more than the magnitude of work in irreversible expansion, whether you see with this diagram, or even if you calculate from your formula, you will get the same result. Whether you are using 2.303 nRT log V2 by V1, or P external V2 by V2 minus V1. So in both the cases, whether you are using formula or you are using this graphical method, you will get the same result. Now let's talk about reversible compression and irreversible compression. So all of you are knowing that reversible process can be reversed with the same path by very slow steps, and in finite steps, very slow process. So the path of the process is the same reversible path. This is the initial state, this is the final state. Since the volume of final state is less than the initial state, so this is a compression curve, right? So this is the reversible compression. But in case of irreversible compression, what should be the path? All of you are knowing that irreversible process cannot be reversed by same path. So you cannot move with the same path like this. You have to follow some other path. So the best path, and we can say easiest path, I am not telling that this is the only path, but this is the best path which can be here, that how you are going to compress. So suddenly you increase the pressure, means suddenly you push the piston down, so the pressure suddenly increase. So keeping the volume constant. Remember the concept that when two variables are changing, so every time you have to design the path, and in the path designing you have to make one variable constant, then take the change in other variable, and in other step do the same thing, keep other variable constant, then change the other. So here see, if you suddenly push the piston and increase the pressure from P1 to P2, so this is isochoric, basically isochoric compression, right? Volume. In this case, we are assuming that volume is constant and pressure is increasing. And after that, we are assuming this is the method to evaluate the variables. Otherwise, you cannot evaluate, right? So after fixing the piston, now the gas will homogenize in the whole system, and it attains the equilibrium inside the system and with the external features. So now the path like this. Now this will compress. So this is the isobaric compression, and this is the isochoric. Isochoric. Increase of pressure, right? Means we are changing pressure but the volume is constant. So this time this is the initial state and this is the final state, and this is the irreversible path, right? This is irreversible path, irreversible path, right? Path of compression. So what is the area under the curve? This time the area under the curve is like this. This is the area under the curve. So this time if you compare, the work, so this time the work, magnitude of work in reversible process is less than W irreversible. But this time there is a compression, right? So when there is a compression, the work involved in the irreversible process is more than the reversible. So hopefully all of you are clear. With the help of graph, now you can determine whether in which case the work is more, right? This time we are doing work on the system. So in irreversible compression, more work we have to put on the system, and in case of expansion we can extract maximum work reversibly, not irreversibly. So actually the default process is expansion, not the compression, because humans don't want to put waste his or her energy, so they do not want to do something on the system. Every time what humans want, they want that the system do work for us. So the default process is expansion process. So in the case of expansion, we get the maximum work, we can extract the maximum work from the system is the reversible process, right? So the default process is expansion, not the compression, because in case of compression we have to put the energy to the system, and that is the wastage of our energy, right? So some psychology is also working here to understand this, why we are always using this expansion, and everywhere you will find the statement that in case of reversible process we will get the maximum work, because that we are trying to extract the maximum work from the system. That's why that expansion process is default process. But remember, in case of compression, in case of irreversible compression, you will get you have to put more work on the system, right? See, consider this question for the, comparison of work between reversible and irreversible expansion. Suppose 1 mole of an ideal gas was subjected to expansion at 300 Kelvin in the following ways: reversibly from 2 atm to 1 atm, and irreversibly from 2 atm to 1 atm at constant external pressure against constant external pressure 1 atm. Or this can be written in this form: from 2 atm to 1 atm at constant external pressure, without mentioning irreversibly. So whenever this term will come, constant external pressure, anywhere in the question, immediately you understood, okay, the process is irreversible. The process is irreversible. So these are the indicators through which you can identify whether the process is irreversible or reversible, right? W reversible is equal to minus 2.303 nRT log P1 by P2. P1 by P2, right? So from 2 atm, so P1 is equal to 2 atm and P2 is equal to 1 atm. It is given. So you can put here 2.303 into 1 mole into 8.314 joules per mole per degree Kelvin. Units are very important here. And temperature is 300 Kelvin into log 2. And log 2 is equal to 0.3010. So if we multiply, see, first Kelvin cancel, per mole cancel, so you will get the answer in joules. So 2.303 multiplied by 8.314 multiplied by 300 multiplied by 0.3010. So this is 1728. So this is equal to minus 1728.98 joules. So you can write minus 1.728 kilojoule, right? So this is the work extracted from the system. See, negative means work is done by the system, right? By the system means work is done by the system. Negative means energy of the system goes down. So work is done by the system. Done by the system, right? Now W irreversible. So W irreversible is equal to, I have given you the formula, minus P external nRT by P2 minus nRT by P1, right? So see, P2 is equal to 1 atm, P2 is equal to 1 atm, and P1 is equal to 2 atm, it is given. And RT are constant. And P external is given 1 atm. P external is equal to 1 atm. So this time minus 1 atm into nRT by 1 by P2. P2 is 1 minus 1 by P1 by 2. So this is minus 1 atm and multiplied by nRT and this is multiplied by uh, 1 by 2, 1 by 2, right? So now what is the unit here? This is ATM. Okay, so this is cancel. So minus 1 mole into 8.314 joules per mole per Kelvin, and temperature is 300. So we have by 2, by 2. So 8.314 multiplied by 300 divided by 2. So 1247. So minus 1247 joules, or we can say 1.247 minus 1.247 kilojoule, right? So from this you can clearly say W reversible is more than W irreversible, right? More than W irreversible. So in this way, with the help of formula, you can also prove that this in the case of reversible, the magnitude of work is more or compared to the irreversible process, right? Now, one homework for you people: do the same calculation. Do the same calculation. Do the calculation for work in the above case at 300 Kelvin, and for 1 mole right? Number 1, compression from 2 atm 1 atm to 2 atm, 1 atm to 2 atm reversibly, and compression from 1 atm to 2 atm against constant external pressure, 2 atm, right? Do the calculation for work in the following, not above, in this case. In this case, for 1 mole of ideal gas, number 1, compression from 1 atm to 2 atm reversibly, and compression from 1 atm to 2 atm against constant external pressure 2 atm, right? So this is homework. All of you should calculate and compare this time, right? I have shown here one calculation and one comparison.